All right, so 10.1 is about areas of parallelograms, and we'll get into triangles. But areas of parallelograms, this is generally a pretty easy formula. There are some little twists that we'll address, but we need to make sure that we understand these formulas that I give you today, because they are going to be then the foundation for upcoming formulas. Everything kind of comes back to the area of a parallelogram. See if I've got. Let's see if I had a. Definition for area. So area is the square units of two-dimensional space that an object encapsulates or an object takes up. Okay, the square units of two-dimensional space that an object encapsulates or consumes or takes up. Okay, and we have a postulate. Okay, so we can't prove this, but we have a postulate that says the area of a square is the length of a side squared. Okay, the area of a square is the length of a side squared. Okay. So a lot of times we'll say A, capital A for area is equal to S squared or S times S, however you want to view it. But that's a postulate, can't prove it. It says the two figures are congruent and they have the same area. If they're congruent, then all the components that fit into the formulas for area will be the same components. Therefore, they will evaluate the same way, so they'll have the same areas. Okay, we know that, right? That's not earth-shattering information there. The area of a square, side times side. Okay, and basically what happens then is when I want to talk about finding areas of other shapes, it's ultimately how many of those side-by-side squares can you fit into another shape. Okay, and that's going to be the process that we go through. In order to do this, we need to know what an altitude is. We've talked about altitudes for triangles, okay, and we talk about altitudes for other shapes. It's the same idea. An altitude, okay, will go from a or to a base, okay, starts at any segment. Says a to a base is any segment perpendicular to the line containing the base from any point on the opposite side. Okay, so basically what you're going to do is you're going to find opposite sides. You're going to choose a point on one of those opposite sides, and you're going to then draw a segment that is perpendicular to the opposite side. That segment is then classified as the altitude. Same thing happened on triangles. Okay, but triangles, we don't have opposite sides. We have opposite vertices. Vertices are opposite of sides. So we go from a vertex perpendicular to the opposite side. But here, okay, if I start at, so this is our parallelogram over here on the left, I can start anywhere on this side. So we're going to start at A and go perpendicular to the opposite side. I can start at B and go perpendicular to the opposite side. Or we're going to start at C, and now I can't go perpendicular to the opposite side because perpendicular, if I draw essentially any segment from C, will not intersect this opposite side, right? So that's why this phrase says to the line containing the base. Okay. Now, what we would do here is we would consider that side there a base, and this side here a base. Because when we draw those altitudes, it's actually perpendicular at A, at B, and C as well. Does that make sense? Okay, so there's no distinction on which side we started from and which side we finished at to construct that altitude. But each one of those dark dotted lines, the vertical dotted lines, is considered an altitude. Okay? And those are not the only ones. There's an infinite number of altitudes we could put in there, but those are three of them. Okay? And those are the three that you would see and use the most often. Okay? The two from A and B are predominantly the most useful. Okay? And a lot of times we might even put both of them in and use both of them. Okay? Over here, what kind of shape is this over here? Probably a trapezoid. We just don't, I mean, we could probably assume the top and bottom are parallel, but these sides obviously are not. But going from A, B, or C, perpendicular to the opposite side, we can see then that those dotted lines would be altitudes. We can also have, this could be another one. That could be another one. Okay, as long as they go perpendicular to the line containing the opposite side. But those are our altitudes. Okay. Now, basically, what we're gonna come up with here in adding to this definition is that we want our altitude to be between parallel sides. Okay. Would you agree that the way that we drew it on the left in that parallelogram, that opposite sides were parallel, and then the altitude is the distance between those two? Does that make sense? On the one on the right-hand side, again, we have the parallel lines being the two lines that the altitude is being drawn between. Generally, based on the shapes that we come across, they say going from a point perpendicular to the base, generally all bases are identified as the parallel sides. Okay, so that might be a way of distinguishing where our altitude is. The area of a rectangle equals the product of its base and height, b times h. I'm going to use b and h, okay? Maybe previous courses you've learned it is, what are other formulas that you've learned for rectangle? Length times width, okay? Usually length being the longest and width being the shorter distance. We use base and B for base, H for height, which is really for altitude. And we'll do that because of how all of our other formulas are determined off of this thing. If I use L and W, you don't see the connection between the area of, say, a rectangle and the area of a triangle or the area of a trapezoid or something like that. So area equals B base times H altitude. Okay? And the proof of that, it's a theorem, but the proof of that would be, all right, well, can that thing be sectioned up into squares that are side-by-side lengths? And you could find out that through doing that, you could count, let's do it this way. Let's go, like if I broke this up into sections like this little square here, let's say we broke it up to side S and side S. That little square would be S times S, or S squared, right? Okay. Now we would have 1, so that 1, 2, 3, 4, 5 of those, right? So we have but then we have the same 5 in the second row, right? And then we have the same 5 in this last row. And you don't necessarily need to write this, okay? But that would give me 15 S squared, right? Does that make sense to everybody? Okay. Well, wouldn't this be 3 S's? And wouldn't that be 5 S's? What can I do with those two things to get the same 15 S squareds? Multiply them, okay? And if this is in B, and then this is H, multiplying those would give me 15 S squared, or give me B times H, which is that area formula. That kind of makes sense on how that would work? Okay. But base times height, base times altitude. You're gonna hear me, and it's hard to fix. It's hard to fix by just throughout my entire life, your entire life. When they say h in a formula, you usually refer to it as height, right? Just understand that height doesn't have to be a vertical distance. It doesn't have to be up and down. Okay? If I am, let's say I'm standing, okay, that would be my height, correct? Let's say 6'1". Okay? If I'm laying down, is that still my height? Huh? Yeah, you're still, now over time, like your vertebrae decompress and you do get a little bit taller. You're taller in the morning than you are at night, right? Okay. But in general, if I'm 6'1" when I'm standing up, I'm 6'1" when I'm laying down. Okay. So that needs to be understood, that it's not always a vertical distance that h is representing. Okay. And we'll see that here in a moment when we talk about this figure. So a parallelogram, try to show you why a parallelogram is the same exact formula as a rectangle. Okay. Now, one thing to understand is that a rectangle is a parallelogram, right? A rectangle is a parallelogram. But the area formula for a parallelogram is BH. Okay? BH. Now, B, the base, being the two sides that the altitude is drawn between. Okay? So here, in this picture, the 5 would be your altitude. 12 is a base, and this is also a base down here. Is that okay with everybody? So if I'm trying to find my area, it's B times H. It's 12 times 5. It'd be 60. Okay? But let's talk about why it's B times H. Okay? If I draw that altitude where I have it drawn right now, it takes my parallelogram and it creates a right triangle there, right? Okay. Now that right triangle, I've got the right angle out here on this side, but it would also be on this side. Okay. And because I chose to draw it from this vertex, this actually turns into a right angle as well. Okay. I'm going to take a pair of scissors, and I'm going to chop this off right here. I'm going to chop off this right triangle. Okay. And once I chop it off, I'm going to slide it over here. I'm going to glue it back down. So now that became a right angle right there. Does that make sense? And now what should be missing here, once I took my scissors and cut this off, is that this is actually gone now. Okay? But that area, I can't, laws of physics tell me I can't destroy matter, right? Can't create matter. So that area, even though it is not on the left anymore, I redistributed it to the right. And now, because of where the right angles are, if this is a quadrilateral with 3 right angles, it's a quadrilateral with 4 right angles, right? So what's the area of that new shape? Still 60. It's base times height now, right? It's a rectangle, is it not? Okay. So if it's a rectangle there, the formula must be B times H. So then that formula must stay constant or consistent when it's a parallelogram like this one. Okay? So B times H is the area formula for a parallelogram, because every single parallelogram you come across, you can redistribute the area and construct it into a rectangle. Does that make sense? Okay. Now, what stinks about this is that altitude is one of 2 altitudes that could actually be drawn. Huh? This is the static picture of what I'm trying to argue here. And I'll show you something in GeoGebra that I think will make more sense of it. But this is usually a picture that they're going to draw in like Math Excel or something like that, for you to get it and understand what's going on. We said that when we draw an altitude from a point perpendicular to the opposite side, that was called the altitude. The opposite side was a base, and for a parallelogram, the base are the parallel sides. But for a parallelogram, how many sets of parallel sides do you have? You have two. So ultimately, you have two sets of bases. Okay? The easiest one to see and to visualize is this one right here. This is what we just did. Okay? That's the setup when you just let the top and the bottom be your base. The way I like to think about it is, if I had this on my desk, if I had like a tanagram wood cut out of a parallelogram, and somebody asked me to find the altitude, I would set that red. I would set that red segment on my desk, let the parallelogram go up in the air, and then measure from the top to my desk, right? Does that make sense? And that distance would be that dotted blue line, which would be my altitude. Okay? However, could I let that be my base? Because that's parallel, right? So the idea is because that's parallel to this side here. If I go from that point right there, or that point right there, or that one right there, and I want to construct the altitude, well, that's going to go to the opposite side, perpendicular to the opposite side. So it might be that distance, or it might be that distance. So those would be altitudes. Does that make sense? Okay, those red lines or that blue dotted one. You can see how that would relate. So we got this green one right here. That green one right there is just the superimposed image of what that one on the left figure was. Okay, so you got the green altitude was one option, but you also got the dotted blue one as the other option, and they're probably going to be different values. Okay, unless it's a square, and then we're not using this specific formula on a square or technique. Here's where I think it gets a little bit easier to understand. If I look at this right here, okay, would you guys all agree that this distance right here would probably be the best altitude to draw? That cool? We understand that? Okay. So what I'm going to do is I'm going to see if I can get GeoGebra to tell me that distance. So I'm going to go from a point perpendicular to one of these lines. I have to do this. Okay, so we'd be looking at that black distance. That would be an altitude, right? Everybody okay with that? And if I ask GeoGebra to find that distance, it will sit back whatever that value is. Now, that would be kind of the most maybe convenient, I think in the setup of this parallelogram, the most convenient altitude to use, okay? That would make A to B a base, or D to C a base, right? Okay, but we can do this. I can take that parallelogram, I can actually rotate it to where now let's see if I can get this to do it right. Now, let's say that the red segment is the top of my table or something like that. Does that make sense? Can you visualize that A prime down here would be another way of describing the height of this parallelogram? Does that make sense to everybody? So in order to find that, what I would need to do, and I'm going to do it this way, I'm going to tell this line to be the y value of b prime. Okay. So I can do something like that. Is that okay with everybody? Now, if I want to find the altitude, that way, I'd go from A prime straight down to the top of my desk, and it'd be that distance. Find that intersection point, figure out that segment, and now that would be an altitude. Would you guys agree that A prime to G is probably bigger than that distance right there? Okay, so I'm going to find that value. So A prime to G is that distance right there, and D to F is that distance there. They are two completely different values. Everybody okay with that? All right, but if I use DF, I'm going to say DF, so it's going to put 2 in here for DF, and I multiply it by the base that DF is being drawn to. So that would be segment AB, right? So multiply that by AB. So right there is base of AB times the altitude DF. And I hit enter. It's going to tell me, I got to search for it, but it's going to tell me that area, so that right there, DF times AB, that area is 16. Is that okay with everybody? Now, when I rotate, and this is something that maybe is a reason for the chapter 9 coming before this chapter, but if I rotate this, does that change any area? No, it should still be the same thing, right? If I take a piece of paper, which is 8 inches by 11.5 inches, and I rotate it, is it still 8 inches by 11.5 inches? So it's still going to have the same area. It's still going to encapsulate the same area. So what I want to do here is I want to take A prime to G, that would be this altitude, and now I'm going to multiply it by this base of, so the base is still this small segment, B prime, C prime. So multiply that by B prime, C prime. Neither of those are really nice numbers. But when I multiply them together, does it still give me 16? Does that make sense to everybody? So if I look at that distance right there, which is 2.828 times 5.6569, gives me the same thing that 2 times 8 would give me. Does that make sense? Okay. In several problems, what they will do is that they'll say, okay, you've got this area to be 16, and I'm telling you that this segment here is 2.828. Can you find the length of this altitude? Well, if that's the case, if this blue one is area is base times height, and I know from this one that the area was 16, can I put 16 here? Can I put this 2.828 number there and solve that equation for H? And that give me my remaining altitude? Is that all right? Okay. So you'll definitely see a question in your homework like that. What they like to do is, in practice problems, they just give you extra distances that you don't need. So in question A there, what two things am I going to multiply together? 4 and 5. 4 is the altitude, 5 is the base. Okay, so we get 20. In B, what two distances are you going to multiply together there? 3.5 and 2. Okay, so you always go the base that the altitude is drawn to. Okay, so 3.5 times 2, and we get 7. So when we do this though, and this is just something always to remember, so 4 inches times 5 inches, okay, and this is called dimensional analysis when we deal with units. Units are commutative just like numbers are. So we can rewrite this as 4 times 4 times 5 times inches times inches. And when I have like bases, what do I do with my exponents? these are like bases, don't you add your exponents? And that's why it becomes inches squared. We talk about area always in square units. So here is why this chapter, I think, comes or should come directly after what we just did. Okay? Do we have the ability to find the altitude here using knowledge from the last chapter? Okay? So what kind of triangle jumps off at you when we draw this altitude H here? 45, 45, 90. So in a 45, 45, 90, this is your n radical 2 side, correct? So how do I find H then? Okay. I'm going to divide both sides by radical 2. And once I do that, that's going to give me this, but then I need to rationalize that, right? I know some of you have recognized the pattern. Oh, this gives me 12 radical 2 over 2, which the 12 and the 2 cancel, gives me 6 radical 2. Some of you recognize that if this is a whole number, then basically we split that in half and multiply by radical 2, and that will give me the leg of the right triangle. And that's fine. That'll work every time. So we have 6 radical 2 as the n, which is the side length of our right triangle, which is also the altitude. So n is the side length of the triangle, but h is the altitude, and they are shared, right? They're the same segment, so n is h. So now, if I go area is BH, B is 31, H is 6 radical 2. What's 31 times 6? 186. And then I multiply by my radical 2. And this would be whatever our units are squared. Is that all right? Okay. What if they didn't give me 45 degrees? What if they told me it was 40 degrees? What would I have to have used? SOHCAHTOA. Okay. Let's see here. Every triangle, no matter what, and I'll start with an easy one here. If I start with a right triangle, okay, and take that right triangle, oh, that was terrible. Let's see if this will work. There you go. If I take that right triangle and do that, okay, what did I just create? Rectangle, right? Okay. Now, is that triangle right there the exact same as that triangle right there? So what would be the area of that rectangle? What would be the formula for it? Careful. Rectangle. Area of the rectangle. Base times height. Okay? So then the area of just that thing right there would be 1/2 that, right? Does that make sense to everybody? Okay. So for a right triangle, we see that. But what if it's not a right triangle? That's always the question. What if it's not a right triangle? Well, we should be able to do a similar thing. So we agree that is a non-right triangle, correct? Okay. So I'm going to have to do a little bit of configuration here, but let's say that we take, just to get this to work, I got to find this point down there. Bless you. All right, so what if we take and look at that blue triangle, and then we will look at, well, that blue triangle, and let's find the midpoints of these things. Midpoint of that side. Let's see here. So would you agree that these are two right triangles? The way I constructed this, that was a right angle. So those are two right triangles, okay? Looking at the overall triangle, trying to figure out an area formula or an area relationship for that. If I take this purple or pink one and rotate it around there, does that become that? Does that make sense? Okay. So now, if I do the same thing with this blue one and rotate it around J, and I do that, does that collectively give me now a rectangle? Okay. These were right angles here, so that's a right angle, that's a right angle. We could do the math to figure out that's a vertical line and that's a horizontal line, so that's a right angle. So it's got to be a rectangle. So the area of this thing would be B times H. Okay. But when K is 0, okay, so there's no rotation here. Okay. That's just that triangle, so those areas would be half of what we just had, right? So no matter what triangle we work with, the area is always 1/2 BH. Okay? 1/2 BH. Okay? H being the altitude. And again, and this is where people struggle a lot with triangles for whatever reason. You've seen that formula before, correct? 8th grade math, you probably did 1/2 BH. Probably did in 7th grade math, probably did in 6th grade math. But generally, the number one triangle that you dealt with in those courses was a right triangle, so it did not matter what B and H were. Okay, they were the legs of your right triangle. Here, we're going to have to realize that H is going to be one of these altitudes that may not, and probably most of the time will not be, a leg of your triangle. Okay? And that's kind of what all of this is talking about here. I don't want to read through that with you, but you just have to be very cognizant, very aware of what H is. It's not always going to be just the values that they provide you with in a problem. Okay. Now this one does. Okay. Here basically says you want to make a triangular sail like the one on the right. How many square feet of material do you need? Okay. I guess it's not to the right, but it's below. But this distance right here, get a different color here. This distance right here would be what component to my formula? It's this 12 foot 2 inches. That's my height, right? Okay. So H is 12 feet 2 inches. Okay. And base then is 13 feet 4 inches. Okay. And all I want to do here with this one is just to make sure that we understand how to do this, because right now it's in feet and inches, and that might be troublesome for us to multiply the way that it's written. Okay? If I go 12 feet 2 inches, how do I write that as a decimal? 12.2? Why not? Because it's out of 12. It's not at feet are 12 inches are the individual components that make up 1 foot, right? So we need 12 1/12 to create our foot. So this 2 is representing essentially a sixth of the next foot, right? So this is really a couple different ways you can write this. 12 1/6 feet. Is that okay with everybody? This would be 12, okay, and 4/12 would be 1/3 feet. Is that okay with everybody? So 12 1/3 feet. Now, if I'm going to go area is 1/2 BH, what I want to leave on what kind of numbers is like 12 1/6? What kind of number do we call that? Nope. That's a mixed number, okay? Which mixed numbers have no practical algebraic purpose, okay? They are useless to us algebraically. I need to do this. I need to make that, what is that, 12 times 6? What's 12 times 6? 72. So I need to make that 73 sixes. What's that called? What kind of fraction is that called? Improper, right? Okay, because the numerator is bigger than the denominator. And I will change this one here to, what, 36, 37 thirds. So there's B and there's H. Is that okay with everybody? And now this would be 1/2. So 1/2 times B times H. So now 73 times 37. Probably going to get a calculator for that. Just to quicken things up here. 73 times 37. 2701. And across the bottom, that's going to give me, what, 36? Now, if I want to see if that reduces, all I got to do is see if 2701 is divisible by any of the factors of 36. I'm just going to try 9 real quick. Nope. Okay. Is that something we can do? And that would be feet squared now. Okay, now if you wanted to, you could take 2701 divided by 36. Give me that right there. So that would be 75 complete square feet. Does that make sense? Okay. Does anybody know how I get the square inch part now? Multiply what by 12? This is square inch. This is right now. This would be in square feet. Okay. So I'm trying to get the portion of the 76th square foot, right? So I'm going to subtract 75 from that number right now. So that's how much of the next square foot I have. Okay. But if I want that in inches, or multiply it by 144. We'll get in. No, it's not, because that's going to be. Well, we got 5 minutes left. That's going to be an entire discussion about how we go from dimension to dimension. Okay, from square feet to maybe square inches, that kind of stuff. Right now, that would be fine with me. I'd be okay with that. There's other ways of doing this. Could I take in that 12 feet 2 inches and say, okay, well, 2 divided by 12. Is that decimal there? The only reason I didn't do that is because I knew it was going to be repetitive, right? It's going to be a repeating decimal, and then I got to truncate that at some point. I got to shorten it at some point, and then I'm off with my area. But this has no error in it. Okay. No homework tonight.